Hello, today we're presenting about our project SpotOn, an intelligent multi-camera person tracking and analytics system, implementation and deployment as a part of the software engineering for AI-enabled system course. So, traditional multi-camera surveillance face significant challenges, including the labor-intensive nature of manual tracking, inherent human error, and the technical difficulty for re-identifying individuals across the different camera views due to the variation in appearance, lighting, and occlusion, and these limitations often lead to the operational inefficiencies and potential security gaps. So to address all of these challenges, we have developed an AI-powered system that automates the multi-camera person tracking. Our solution intelligently maintains the consistent individual identities across the network of the cameras and provide a unified spatial visualization of the movement, significantly enhance the surveillance capabilities. The primary business objectives driving into our system are to enhance overall safety and security, improve operational efficiency throughout the automations, provide a unified and clear visualization of the activities, reduce time needed for incident investigation, and enable optimized resource allocations based on the analytics generated. So let's get started with our first sections, the ML implementations. So we began by designing a comprehensive machine learning canvas, which you can see here. This canvas serves as the foundation blueprint for our entire system, meticulously outlining every stage from initial problem definitions and data requirements to the process, expected outputs, and evaluation metrics. So diving into the canvas, our problem statement and business objective column clearly identify the core issues like multi-camera tracking, complexity, and re-identification difficulties, alongside our goal of boosting security, efficiency, and provide automated unified trackings. The input data sections of our canvas detail the necessary components like the multi-camera RGB video feeds, specifically using the MTMMC dataset for initial developments and crucial camera calibration data in the form of homography metrics, all stored on the AWS S3 and characterized by the real-world variations. Our processing approach involves the back-end batch processing pipeline orchestrated by the FAST API, and this pipeline sequentially performs the person detection using the faster RCNN, intra-camera tracking with bot sorts, conditional features extraction, and cross-camera re-identification using the clip, and finally a spatial mapping onto the unified view. The system is designed to produce the several expected outputs for the UI. This includes annotated video feeds and a unified map visualizations. Real-time updates are delivered via the WebSocket JSON payload, and historical tracking data is persistently stored in the timescale DB database. Finally, our success criteria are twofold. Offline AI model metrics such as the AP for detections, the MOTA for tracking, and rank 1 for re-identification, complemented by the online system and business metrics like efficiency gains, response time reductions, and user satisfaction to holistically evaluate our performance. For the model training, we initiate through data explorations and pre-processing, and this involves an exploratory data analysis to understand the dataset structure, frame count, annotation distribution, and to perform essential quality check on the MTMMC dataset. Our EDA reviewed key data characteristics by the image are loaded as the BGR numpy array via the Open Series. Annotations are passed from the text files, and the original image dimensions were consistently 1920 x 1080 pixels in our sample data. The preprocessing pipeline detailed in our codebase begins with the loading image and annotation using a custom MTMMC detection datasets. We then convert the images from the BGR to the RGB formats suitable for the touch vision models and resize them to a target width of 640 pixels, resulting in 640 x 360 dimensions while maintaining the aspect ratio. Continuing the pipeline, images are converted to the PyTorch for 32 tensors and scaled to 0 to 1 range, followed by the standard ImageNet normalizations. For training, we apply random horizontal flipping and ground truth bounding box are formatted to the XYXY, whereas the TV tensor bounding boxes with a custom correlations function handle the batching. We selected the faster RCNN with the ResNet 50 backbone and feature pyramid network as our person detection model. And this is the robust two-state detection with the region proposal network. And first identify the candidates region and the ROI head, then classify these regions and refine the bounding boxes. The faster RCNN model was initialized using the pre-trained ImageNet weights, and we then modified its classification head with the new faster RCNN predictor tailored for our two classes, the person and the background, and configured the ResNet 50 backbone to fine-tune its deeper layers for improving task-specific performance. The training process is orchestrated by a dedicated script that loads the configuration, set up the ML4 for experiment trackings, and involve our core PyTorch training and validate engines, ensuring a structured and reproducible workflow. For our initial sample run, key hyperparameters included 5 epochs, a batch size of 2, the Adam W optimizers with initial learning rate of 0.001, and a state LR scheduler, and this testing while conservative allow for the efficient initial model evaluations. During training, standard faster RCNN loss components are calculated initially. The process leverages the configurable device port like CPU or CUDA, enable the automated mix precision on the CUDA for speed and memory efficiencies, and implement checkpointing after each epoch, and saving the base model based on the wall MAP of the 50. Our validation methodology involves a random 20% of the data split for the validation set and performed by the MTMMC detection dataset. Validate occur at the end of each training epoch and calculate the average validation loss and the standard COCO style MAP metrics using the torch metrics. Here are some key metrics from our initial sample fine-tuning run, which used a subset of the data and ran for a limited number of epochs. As you can see, we tracked valid loss components and evaluation metrics like eval of the MAP of large and our eval of the MAP that reached 0.6522 and the eval of MAP 50 was 0.8954, indicating a good performance at detecting the person with reasonable overlap. The close training collision loss suggests minimal overfitting on these subjects, though we note as the eval AP of the person's metric require further investigations. To ensure code quality and correctness, we implement unit tests using the PyTest, and this test mirroring the code structure validation key functionality within the dataset, handling metric calculations, training runner, and utility functions, employing the mocking where necessary to isolate the components. In our fairness analysis, we identified several potential sources of the bias with the MTMC dataset, and this include demographic imbalance related to the geographic origin and clothing style, environment bias like the valley lighting and camera viewpoints, and potentially annotate bias from the labeling processes. Since the direct fairness metrics often require sensitive attributes unavailable in the MTMC dataset, we propose a conceptual approach for using the proxy analysis, and this involves evaluating performance disparity, for instance in the re-identification accuracies across a group defined by the observable characteristics like lining conditions or the bounding box size. To mitigate any of the detected bias, we consider a range of strategies, and this includes the database methods like targeting augmentations and resampling, model-based approach such as the adversarial debiasing, post-processing techniques like group-specific threshold, and operational strategy including user training and continuous monitoring. For the model selection, we conduct a systematic experimental using the ML4, compare 4 distinct person detection architectures. First, we have the faster RCNNs, 2 variants of the RTDATR, and the YOLO-based model. We log key parameter and performance metric for each run as shown in the MLflow UI screenshots here. The parallel coordinating plot from the ML4 provides a visual overview of the quantitative performance comparisons, and it highlights how different models perform across key metrics such as the mean average precision or the MAP, the processing frame per second or the FPS. And this table details the specific performance metrics, notably why RTDTRX achieved the highest overall of the MAP and speed. Faster RCNN demonstrated significant better performance on the medium-sized object and detected considerably more persons overall, indicating the superior recall. Based on this finding, we selected faster RCNN as our baseline model, and this decision was driven by its superior medium object performance critical for the surveillance and higher recall indicating by more total detections, better observed quantities, stabilities, and the acceptable processing speed for our back-end batch processing pipeline. And to understand our faster RCNN model predictions, we implement a gradient weight class activations mapping or GradCam. And this technique is suitable for the CNN's generative visual heat map, like highlighting the image regions and most influential for a specific classifications. We utilize the Captain library for this. Here's a GradCam example from the factory scenes. The heat map strongly highlights the torso and upper leg regions of the detected persons, indicating the model's high confidence based on these features. In the campus skin with the smaller, more distant person, the GradCam heat map correctly concentrates the upper body and the head regions, and this demonstrates the model ability to identify the relevant features, even when the subjects occupy fewer pixels. Similarly, in this third example of the heat map, again focus on the core body or the torso, focuses on the core body of the detection persons within the activation relatively contained within the person's bodily, and these visualizations are invaluable for verifying expected model behavior and aiding in debugging. Beyond visual explainability, we design a mechanism to provide a human understandable textual reasoning for the individual predictions, and this uses the heuristic rules based on the model's confidence score and incorporate the availability of the GradCam visualization to offer a more comprehensive explanations. This is the textual reasoning generated for the factory scene detection we saw earlier. It states the person classifications, the high confidence score, interpret this as a strong visual evidence, and directs the user to the associate GradCam focus on the insight into the influential images regions. Focus on insight into the influential image regions. Here the reasoning for the first campus scenes. Again, it highlights the high confidence and refers to the GradCam visualizations, providing specific bounding box coordinating for the user to reference the influential region identified by the models. And for the final campus scene, the reasoning follows the same structures, confirming the model decisions and providing a pointer to the visual explanation. This mechanism successfully generates a practical, human-readable explanation for individual detection decisions. We have deployed our system as a service using the Fast API, a model high-performance Python web framework. The backend is structured within the main application entry point and several core service classes like the pipeline orchestrator service to manage the processing tasks. The primary REST API endpoint for initiating a task is supposed to pair to the API/v1/processing task/starts, and it accepts the environment ID and upon success return a 202 accept status with the task ID and the URLs for status checking and WebSocket connections. To monitor a task, client can make a GET request to the API/v1/processing task and put the task ID/status, and this endpoint return a current status, progress percentage, and any relevant details for all the error messages for specify the processing task. For the real-time update, client connected to the WebSocket endpoint using the WS/tracking/the task ID, and this team provides the two main message types, the status update, mirroring the REST status response and status and tracking update, which contain the detail per frame tracking metadata including the bounding boxes, the global ID, and the map coordinates. We validate the deployed service using the Python test client that simulates a front end, and this client log shows a successful post request to start a task followed by the connection to the WebSocket URL and reception for the structure status update and tracking update message. Complementing the client-side validation, this server log from our Dockerized backend confirms the successful handling of the incoming HTTP request, WebSocket connection establishment, asset downloads, AI model loading, and subsequent frame processing activities. Our backend design incorporates several scalability considerations, the stated API endpoint suitable for the horizontal scaling, background processing to keep the API responsive, the service separation for modularity, efficient data flow using the lightweight JSON metadata, optimize the AI inference, and containerize with the Docker for consistent deployment.
Section 2 UI Model Interface. Moving to the UI, this mockup illustrates how AI-driven insights are present. Key features include live camera feeds with AI-generated bounding boxes and person IDs, a tracked people panel leveraging ReID, a unified map visualization with projected parts, and a detailed position tracking table. To facilitate AI model improvement, our UI design incorporates user feedback mechanisms. These include confirmation features within the Track People panel to refine the VAD, and a general feedback button allowing users to report broader issues, capturing relevant context like timestamp and camera view. The interface between the UI and the backend begins with a post request from the UI. The payload is a simple JSON object containing the environment ID that specifies which dataset or camera group to process. Once a task is running, the backend pushes the tracking data to subscribe UI clients via WebSocket. This example shows the overall structure of a tracking update message and containing a frame index, scene ID, timestamp, and a camera's object holding data for each active camera. Within the camera's object, each key is a camera ID. The corresponding value contains the image source, which is resolved to a full URL by the frontend, and an array of tracks detected in that camera's current frame. So each object in the track array represents a detect person, providing their temporary tag ID, their persistent global ID from VAD, bounding box coordinates, detection confidence, class ID, and crucially, their projected map cohorts on the unified 2D map. Upon successful initiation of a processing task via the REST API, the backend responds with an HTTP 202 accept status. The JSON payload, as shown here, includes the unique task ID for the newly created task and the related WebSocket URL for the client to connect to for real-time updates. This sequence diagram clearly illustrates the interaction flow. So the UI sends an HTTP post to start a task, and then the backend responds with task and WebSocket details. Then the UI asynchronously establishes persistent WebSocket connection for receiving ongoing real-time tracking and status update. We test the backend API and WebSocket interface through the direct integration with our developed front-end React application. So specifically, the group view page components. This allows for end-to-end testing from task initiation to the display for real-time tracking data. In our first test scenario, the group view page successfully loaded. Initiate a processing task via an API call to the backend, receive a valid task ID and WebSocket URL, and establish a WebSocket connection as evidenced by the active camera feeds and initial data rendering. With the wheel tab active, so our second scenario validates the real-time receptions and display of tracked updates. The UI correctly rendered numerous green bounding boxes with associated global IDs around detected individuals across all 4 active camera views, as you see in the picture. The scenario 3 focuses on the map visualization, as tracking updates message containing map cohorts were received. So the UI accurately plot these as colored dots, as you see in the picture here, in the respective camera quadrants on the map, correctly scale and style according to our predefined camera color map. So during the integration, we encounter challenges such as ensuring correct WebSocket URL, construction, and connection timing, which we solve with stricter sequencing and explicit URL building. We also address mapping back in camera IDs like camera 9 C09 to front-end UI elements like camera 1 by implementing explicit mapping object. Further challenges include resolving image paths as the backend provides only file names, which the frontend solves by constructing full URL using a base path. Additionally, the real-time map coordinate scaling for resizable UI quadrants was handled by using a resize observer and dynamically calculating scaling factors. In conclusion, we have successfully designed, implemented, and validated an ML pipeline for multi-camera presence tracking, selected an optimal detection model, developed explainability features, deployed the system as a scalable service, and integrated with a functional UI, overcoming several practical engineering challenges along the way. And here's the demo video from the UI side. And this is a page where you select the zone to build a camera feed. So, okay, you can see the frame streaming on the screen, and there may be some lag at this time. You can see the button box of the detected person and the coordinates of people showing on the map at the right panel. You can switch to build a single video feed too, like this. And here's the stop and play button. Okay. And here's the backend local server log. So you can see that the model is processing in the background and sending back data frame by frame via WebSocket message, like the track ID, the global ID, or the map coordinates. Okay, that's over all of our project. Thank you for watching.